Hello, everyone. My talk is about Provably secure federated learning for edge computing. So let's first describe a little bit of technical background about federated learning. Suppose we are given some client. Each client has some data locally. We are also given a cloud server or edge server. This server maintains a machine learning model called a global model. Each client also maintains a machine learning model called a local model. Federated learning is basically an iterative algorithm which repeats the following 3 steps in each iteration. In step 1, the server sends the current global model to the client or a subset of them. In step 2, each client trains its local model based on the current global model and its local data. Then each client sends its local model to the server. And in step 3, the server aggregates the client's local models as a new global model. So federated learning repeats these 3 steps for many iterations. Federated learning is basically a distributed system. Due to its distributed nature, it is fundamentally vulnerable to poisoning attacks. In particular, an attacker can have access to some malicious clients. These malicious clients could be fake clients injected by the attacker into the system, or genuine clients compromised by the attacker. A malicious client can poison its local data, which is called a data poisoning attack. A malicious client can also directly poison its local models sent to the server, which we call local model poisoning attack. Eventually, the global model is poisoned, and the poisoned global model makes incorrect predictions as the attacker desires. So we designed federated learning methods that have provable security guarantees against such kind of poisoning attacks. So before I describe our work, I'd like to first formally define what I mean by provable security. Suppose we are given a set of benign clients and a testing input X. F is a federated learning algorithm. HCX is a predicted label for X. When the global model is trained on C using the algorithm H. Now suppose some clients in C become malicious. We denote C prime as a set of clients, including the malicious ones. HC prime X is a predicted label for X when the global model is trained on C prime using H. So we see the federated learning algorithm H is provably secure if this HC prime X equals HCX for any C prime, such that the number of malicious clients is at most M star. So we call M star the certified security level for X. We propose an ensemble federated learning method, which is the first method to achieve such provable security. Suppose we have N clients. We select K of them uniformly at random and train a global model on these K clients. We can use any federated learning method to train this global model. For example, fedAverage developed by Google. Then we repeat this operation to train N global models. Given a testing input X, we use each of these N global models to predict its label, and then take a majority vote among the N predicted labels as a final predicted label for X. Then we can prove that this ensemble federated learning achieves our defined provable security. So in our evaluation, we define a new evaluation metric called certified accuracy to evaluate such provably secure methods. So certified accuracy at N is a fraction of testing input whose labels are correctly predicted and whose certified security levels are at least N. So certified accuracy at N is a lower bound of testing accuracy when the number of malicious clients is at most N, whatever attacks those malicious clients use. So let's see one experimental result. So in this graph, the x-axis is the number of malicious clients N, the y-axis is the certified accuracy at N. This curve is a fedAverage method developed by Google. And this curve is our ensemble fedAverage. So we basically use the fedAverage to train the N global models. So the results are from the MNIST data set, and we assume 1,000 clients in total. So as we can see, when just one client becomes malicious, the certified accuracy of that average becomes 0. However, when our certified accuracy is still larger than 0.85, when 20 clients become malicious, and whatever attacks those 20 malicious clients perform. So that's what we have already done. And in this AI Institute Center, we are going to do the following. First, so we are trying to develop probably secure federated learning method with deterministic security guarantees, and develop probably secure asynchronous federated learning, and probably secure distributed federated learning without the central servers. And finally, we try to develop theory algorithms and tools to understand and measure the fundamental trade-offs between accuracy, efficiency, privacy, and security in federated learning. Okay, yeah, that's